Think of a standard computational model, like a heavy industrial press. It receives raw material, applies fixed mechanical force, and stamps out a predictable result. The entire architecture relies on a strict assumption. Data is fed into a predefined structure. A programmer selects a specific function, and the system executes that function to generate an output. This is represented by the familiar equation, R equals f of x. The values flow into the function, undergo a calculation, and emerge on the exact same linear plane. The system alters the quantity or magnitude of the input data. But there is a technical limitation built into this architecture. The numerical values might change, but the intrinsic nature, the dimensional class of the object being described, remains identical from start to finish. When computation is restricted to altering how much of something exists, the system remains blind to what the data represents. Identifying the nature of an object requires an operation that can cross dimensional boundaries. We can see a mathematical alternative by looking at fundamental geometry, where operations behave entirely differently based on their spatial logic. Adding a 3 and 2 centimeter length yields a 5 centimeter line, still a one-dimensional object. Multiplying 3 by 5 centimeters extrudes a perpendicular axis, creating a 15 square centimeter area. Multiplying again by a third length produces a 30 cubic centimeter volume. A completely new structural reality emerges. The Aurora model is designed to replicate this exact dimensional emergence. Instead of mapping physical geometry, it applies this logic to computational semantic space. In Aurora, computation is a sequential pipeline of identifying context, assigning roles, evaluating relational laws, and synthesizing entirely new structural dimensions. A semantic dimension in Aurora is a specific property of a system, such as its structure, its function, or its form. Standard processing assumes dimensions align by physical position. Index 1 maps to 1, 2 to 2. But assuming identical physical positions share identical semantic properties is a fallacy. True alignment maps data based on its contextual representation. 1 might map to 2, 2 to 3. This introduces the first critical step of the Aurora pipeline, ordering. Before calculating anything, the system must interrogate the data to assign these roles dynamically. Positional fixity destroys meaning. A tensor's physical address is completely divorced from its semantic function. Aurora relies on 3 foundational semantic roles to achieve this ordering: structure, function, and form. To see how contextual permutation assigns these roles, look at the word key. The exact same data points serve different roles depending on surrounding variables. In a physical door, a key acts as an instrument. Its role is function. In the key to the problem, it is the solution element. Its role is structure. In cryptography, it is the cipher authorizing transformation. Its role is form. In mathematical notation, the permutation function pi sub gamma uses the context variable to resort internal indices to match semantic roles. This context is formed by the mutually conditioned presence of other tensors in the window, defining the space where they acquire meaning. Ordering is the first truly intelligent operation. It is a mutually conditioning hypothesis asking, what role does each component play right here, right now? Once the semantic roles are successfully aligned, the system must determine the specific rule of interaction. Aurora defines this as the spatial law, lambda. This law dictates that the interaction must satisfy an invariant condition of the space, denoted mathematically as R equals 0. The interaction produces 3 states. At E equals 0, contradictory data is rejected. At E equals 2, the mathematically open relationship drifts, searching for completion. But at E equals 1, the data satisfies the spatial law, achieving perfect closure and mathematical coherence. Computation is a rigorous trial to see if incoming data can satisfy the laws of the relational space to achieve closure. An intelligent architecture requires a memory of continuity to prevent forced synthesis when information is missing. When a relationship remains open at E equals 2, Aurora utilizes the carry. The unresolved relational state is packaged and transported horizontally to a new processing window, where it will seek additional context. Synthesis triggers only when closure is achieved at E equals 1. At this point, the resolved interaction is converted into a higher-order unit. Closure triggers a dimensional shift. The locked relationship is synthesized. It moves vertically, becoming a discrete object on a new processing plane. Horizontal movement is the pursuit of meaning. Vertical movement is the crystallization of that meaning into a distinct systemic object. This sequence of operations forms Aurora's master equation for emergence. A new system, S, emerges through the synthesis of a spatial law acting upon a contextual ordering. This synthesis produces properties that do not exist in the constituent parts. In physics, two independent objects each possess mass and position, but properties like velocity, distance, and systemic stability are properties of the relationship between them. The Aurora model identifies the mathematical threshold where a relationship ceases to be an interaction and begins to exist as a stable, distinct entity. Standard computational architectures often transform numerical values without evaluating their systemic role or structural validity. Under the Aurora framework, intelligence is a balance between two distinct movements. The first movement is the patience to carry open relationships horizontally, continually expanding the context without forcing a conclusion. The second movement is the capacity to recognize closure, snapping those coherent relationships vertically into newly emerged cognitive structures. Scaling this architecture creates a network of cascading emergence. It operates identically from the smallest relational data point to the most complex semantic hierarchies. Computation, in this framework, constructs the semantic space where raw data organizes into coherent meaning.